Now we got Robert Robertson. He was actually a highly prolific organic chemist of his time. He made lots of very complex molecules at a time that I can't imagine trying to do the type of chemistry he did. And this is actually going to be simply a combination of two reactions that we just learned. So we're about to get to a section where we're going to learn a lot more about these dicarbonyl compounds. But as you can imagine, these hydrogens will be much more acidic than even your average ketone. Along the way, we can take sodium hydroxide and deprotonate this hydrogen. This equilibrium, as we'll soon learn, is actually much more favorable. This makes quite stabilized anions. So this has more resonance delocalization, so that you could even say that this is going to be softer than normal ketone. And we have the same alpha-beta unsaturated carbonyl compound in the previous slide. So you see, we're going to have to do quite a bit of work. We end up making many new bonds along the way. We see that we're starting with an alpha-beta unsaturated carbonyl compound. We end with one. But this is a case where if we follow the arrows and we think about what steps need to happen, we would definitely expect this hydrogen to be deprotonated first. It's by far the most acidic. And then this is going to be our most reactive electrophile, particularly with a soft nucleophile as an alpha 1,3 beta dicarbonyl. So we're going to make an intermediate enolate. And once again, this will be able to react with water to make a neutral compound. So we've already made one of the bonds we need to make. If we look at the structure, the bond we just made was this bond. Oh, I lost my methyl along the way. Sorry about that. So you can see that this bond we formed here maps onto this bond here. We need to make one new bond, and we see that this actually is coming between 1, 2, 3, 4, 5, 6. Makes this 6-membered ring. So if this carbonyl was 2, that means this methyl was 1, 3, 4, 5, 6. Now all we need to do to finish this reaction is an intramolecular aldol condensation. So normally ketones don't react well with ketones intramolecularly, but intramolecularly we can push this to completion. That means with sodium hydroxide, we're going to now deprotonate the other side of the carbonyl. So I ended up drawing this out explicitly. But in principle, we could have just said from here to here, proton transfer, because all we did was a protonation and then deprotonation again. Now this enolate can do an intramolecular reaction with this ketone. Note that you could have had it attack this other ketone and it would have given the same product because there is a plane of symmetry, so this would have given the same product attacking either one. But since the product has the lower carbonyl reacting, I'm going to show this one as well. Now we've made our 6-membered ring. We have an intermediate alkoxide. We have our ketone. And now what we need to do is protonate this oxygen and deprotonate this hydrogen. So I will just show this as PT for proton transfer. For our final overall E1CB elimination. This gets us to the final reaction. Product. So a lot of reactions take place at once. This overall process, specifically to make these 6-membered rings, this molecule, this is called methyl vinyl ketone, is very commonly used to do Robinson annulations. People even call it MVK in the literature to abbreviate it. And this is called an annulation, and that's because we are adding a ring. So to annulate something is to mean to add a ring onto something else. So I mentioned we were going to talk a bit more about beta dicarbonyl compounds. And I alluded to some of this on the previous slide already because it has an example that kind of fits in between these two examples. So if we look at what we say beta dicarbonyl, this is because the carbon right next to a carbonyl is the alpha carbon, and so the next carbonyl will be in the beta position. And we can have all different types of combinations of our carbonyl compounds. We can have beta diketones, beta keto ester, where one is a ketone and the other is an ester, or you can have beta diesters as well. You could also be having aldehydes of this variant. The main point we want to reinforce, though, is that these are significantly more acidic than your average carbonyl compound. So something like this beta diketone shown has a pKa of around 9 to 10. This puts it more in the range of something like a phenol. We can see and rationalize why this is so acidic, and it's because its conjugate base is very stabilized. So we can move that negative charge between the central carbon atom onto one of the neighboring oxygens and also onto the second neighboring oxygen. So similar to carboxylic acids where you can share it on 2 different oxygens, this will greatly increase the acidity of these carbon hydrogen acids. From the electrostatic potential map, you can get a feel that most of this negative charge resides on the carbons. That's where all this strong red is. But it will still react at carbon for most of the chemistry we will see. Along with this being quite a bit more acidic and the conjugate base being more stabilized, this also means it's going to be a much weaker nucleophile. And we're going to see some limitations on the types of reactions it can do, and particularly with regard to the reversibility of some of these reactions. So let's take a look at what they can do. So we're going to learn a reaction with another name. This one's quite funny. This is a Knoevenagel condensation. So here's Heinrich Emil Albert Knoevenagel. All these guys were around about the same time. And this is nothing more than an aldol condensation. These are going to be the exact same arrows that we've seen before. We're going to be able to make an enolate. This one, of course, is going to now be less reactive of an enolate. It's going to have a higher equilibrium favoring the product. It'll be much less reversible because this is pK about 9 to 10, whereas water is now 14. So now we're going to have a favorable equilibrium forward. But these will still be able to react with things like aldehydes. So something that will be a bit of a distinction relative to the prior aldol reactions that we've learned is that controlling the initial addition versus the later condensation is going to become much, much more difficult. And essentially, we cannot stop the elimination from happening. Because we know that the new hydrogen that formed here, this is very acidic. We know this alkoxide is very basic, depending on where you look. But if this alkoxide is around, or the alcohol has a pK of around 16, this will be able to very quickly do proton transfers. This will still be an intermolecular reaction with 2 steps. Sorry, I don't know why I wrote water. Proton transfer. This will still be 2 steps. It won't be an intermolecular process. And we're going to get back to another enolate. Because the equilibrium of this enolate is so favorable, it's really hard to stop this elimination from happening. Whereas with aldols, we are able to control temperature a bit. For these reactions, you're always going to get the condensation product out. But overall, it's going to be the same logic as we've seen for the aldol for both the mechanism and disconnections, where we would imagine breaking this double bond apart to give now CH bonds in carbonyl compounds. Along the way, we can have actually Michael additions or Michael type additions with a variety of different reactive groups. In addition to beta keto esters and beta diketones, you can also have other strong electron withdrawing groups neighboring the carbon to increase the acidity and also increase the delocalization. So this is going to follow the same logic. Now we have sodium ethoxide shown here as the base. So while this could potentially be reacting at, say, the ester or the ketone, attack on the ketone will be reversible. Attack on the ester would just do transesterification with the same ethyl group. And the fastest reaction of all will just be deprotonating this very acidic hydrogen. Since this is a very soft nucleophile, we're still going to expect this 1,4 addition type reactivity. We're going to have it attack the enolate followed by proton transfers afterwards. So after the proton transfers, we're simply going to attach this group to the 1,4 position and make this new bond. Along with additions to alpha beta unsaturated carbonyls, you can also have alkynes that serve as the alpha beta unsaturated component. So if we walk through this example, we find that we can actually have multiple reactions take place in a row. So frequently this can be controlled by different substituents. We can imagine making this anion that we stabilize by resonance. These are highly reactive alpha beta unsaturated carbonyl compounds when they're alkynes. This would be in ine 08, what people call them. And we'd make this interesting alenic anion as an intermediate. that will quickly be protonated, in this case by ethanol, because that is what is the proton source in this reaction. And we see the product is also an alpha-beta unsaturated carbonyl compound. Potentially, if you had more an excess of your alpha-beta unsaturated carbonyl, you could imagine this doing yet another Michael type addition to do this over again. So again, I would be looking at the relative number of equivalents to determine which pathway is going to be more likely. And also, nitriles can serve on the alpha-beta unsaturated component. Note that this nitrile has a lot of similarity to other type of Michael acceptors like alpha-beta unsaturated ketones. We could add sodium hydroxide to diethyl malonate to make this anion. And we'd be able to attack in the 1,4 position. I'm going to abbreviate the esters as E, just to save a little time writing. Normally, negatively charged nitrogen compounds are viewed as being quite reactive in this class. Remember, this is going to be an sp2 hybridized nitrogen, so it's quite a bit lower in energy, though it'll still very quickly get reprotonated by ethanol afterwards. So again, all of these feature a similar 1,4 bond formation. And this just goes to highlight that the electron withdrawing groups you can have on a double bond to switch over to being an electrophile can be also nitriles in addition to esters or ketones.